I'm not very sure whether recording is on with the screen sharing. I don't see everything here. Yes, the recording is on. Yes, so in this lecture, we will study dynamics of slider. In the earlier one, we studied forward linkage. Now, fundamentally, forward linkage and slider crank are not linked. So the way we analyze the forward linkage, exactly like that, the slider crank also can be analyzed, except for this joint condition. That this is a prismatic wave. It's not a big deal. The same thing can be applied here, and that's quite easy. However, uh, here with a revolute joint converted to a prismatic joint, things actually become simpler, and we can do more. You know that the theory development of slider crank has been driven mostly by the study for engines, and engines have been the driving theme of the industrial revolution and modernity of civilization itself. That was a big deal. So we needed to do more, we wanted to do more, and the mechanism being a little simpler, it was also possible to do more. So here we are keen to go beyond instantaneous dynamic analysis that we did for forward linkage, and here we strive for relationship patterns for continuous cyclic operation. So that is what we will do. So we will not be satisfied with values and numbers. We will go for expressions and functions and explore their patterns. So for the study of dynamics, the preliminary point is the study of kinematic relationships. So here we can see very clearly that r sine theta, the perpendicular distance of A from this line of the slider, is r sine theta, and that is equal to L sine phi. This will. So that relates this angle of the connecting rod with this line, and this angle, the current angle, like this. And from here, sine phi we can represent in terms of theta. And this R by L, that ratio is the mechanism diameter, so that is lambda, and that is less than 1. Because we know that for full circle stability of the crank, we need R to be less than 1. So R by L is less than 1. The typical ratio is 1 by 5, 1 by 7, like that. Okay, so that was the vertical projection. Now look at the horizontal projection. R cos theta will be its horizontal projection, plus L cos phi, its horizontal projection, and together they will make up this piston position, the slider position. That is this. And here we put cos phi in terms of theta. So from here we get sin phi. So from sin phi you know how to get cos phi. That is 1 minus sin square phi. And just we put that. So R we have taken common. So here it will be L by R, that is 1 by 2. The rest is straightforward. So since now we will be simplifying this bracketed expression, it's easier to get rid of this R, open the bracket and do the analysis cleanly. So we throw the R on this side and say x by R is equal to this. The square root has been represented as power half. And then we know that we can expand it in binomial series. As we do that, you should verify this at your leisure, that as we expand this binomial series, we get this kind of thing. And then we do something more. Sine square theta, we can break in multiple angles. So 1 minus cos theta, 2 theta by 2. Then similarly, sine to the power 4 theta, you can do that, you can use that same formula twice to break it into sine cos 2 theta and then that into up to cos 4 theta. Then this whole thing, this power will go off and multiple angle cosine will come. Similarly, this. Okay. So these things you can do, you know the trigonometric formula. And as long as you want to go, you can by doing this. Next term we will have constant cos 2 theta, cos 4 theta, cos 6 theta, cos 8 theta, and so on. Okay. So as long as you want, you can go. But you don't need to go too far because lambda being less than 1, so that also 0.2 or even less, lambda cube, lambda to the power 5, etc. will become extremely small. Okay. So you typically don't need to do, you don't want to go too much, too far. Anyway, now you organize this expression as take all the constant terms, 1 by lambda from here, minus lambda by 4 from here, minus lambda cube times 3 times lambda cube by 64, and so on. And then cos theta terms together, only one cos theta term. And then cos 2 theta terms, one from here you get plus lambda by 4, that is here. Then one you will get from here plus lambda cube by 16, and one you will get from next and so on. Similarly, cos 4 theta terms you can correct. I have written here up to the lambda cube terms because even if lambda is 1 by 5, lambda cube will become 5. So 1 by 125, which is 0.008. So after that, it will become so small that you need not. So L by R is typically 5 to 7. So lambda is 1 by 5 to 1 by 7, something of that sort. And all these coefficient fields, this series, next series, they are all convergent fields. So given lambda, you will get a number here and a number here and a number here. Fine. Now, this is the position relationship. X and y, input and output. Note here that here this is actually the input. Okay. This is the output because the purpose of the engine is to get the power from the reciprocating piston and convert it into the turning of a wheel or turning of a round wheel. So basically, so that is the classical idea of power generation. If you can ensure the turning of a wheel by whatever artifact, that's an input. So this is the input and this is the output. So, except for the kick-starting process, when you turn this in order to start moving. But after power starts getting generated, then this is the driver, this is the driven. After the position analysis is done, then you go to velocity and acceleration. So to differentiate the above thing, this x by r expression. something plus cos theta plus something cos 2 theta plus something cos 4 theta and so on. So as you differentiate this, both sides, this goes up because it is constant. From here you get minus sin theta. From here you get minus 2 sin 2 theta times whatever was inside plus this is plus because the bracketed thing has lots and lots of minus. That is the leading one inside of the bracket. That is why this comes as plus. Otherwise, the derivative of this is minus 4 sin 4 theta. But then, since the bracketed thing turns out to be negative, so this finally becomes plus sin and so on. This whole thing is derivative with respect to theta. So for time derivative, you multiply that with theta. Then when you differentiate this, you get theta dot times derivative of this, which is here, into another theta dot, which is this, plus theta double dot into this whole thing. Now, the important thing here is to work out the acceleration relationships when theta double dot is here, when the crank rotates at uniform, because that is the most preferred way of operation. The output is turning at a constant rate, constant RPM. So when theta dot or omega is constant, then theta double dot is 0. So this whole thing becomes 0. And here you put omega square, get this r on this side, you get minus omega, minus also you take outside common, minus omega square r cos theta plus 4 times whatever for the A2. Then since we have taken minus outside, so this plus will become minus. Then 16 times whatever for the A4 into cos 4 theta and 4. So this is the expression for x square, and it's what expression we want. Now here A2 is found from here, A4 is found from here, that is this thing into 4 is equal to this thing into 16 is A4 and 4. You can find out each other. And again, I have kept up to lambda cube beyond the paragraph. If you want that precise, that accurate, you can. Now for approximate analysis, even this lambda cube term is typically not of great importance. So for approximate analysis, if you did the cube terms also, decaying up to lambda terms, then from here you will get minus omega r is sin theta plus 2 sin 2 theta into lambda by 2. And from here, this term and just this term. So A2 turns out to be just that. So for approximate analysis, this much is enough. For more accurate analysis, you can take one of two. So once the acceleration relationships are settled, so you see x double dot piston acceleration is expressed in terms of the crank speed, crank angular velocity, because the crank's angular acceleration is for uniform acceleration. Now, we go to forces. And when we talk about force motion representation, force motion relationships, you see that out of all the links in this mechanism, it is the connecting rod only which has a complicated motion, because that's only floating. One is frame, doesn't move. Another is piston, moves, only slides, pure displacement, pure sliding, to and fro. And the another is crank, which rotates about a fixed point, does not transfer. There is that point, that fixed point, doing fixed. So always rotation about a fixed point. There is a connecting rod which travels in a very peculiar transition. to the satisfy only floating. So the force motion relationship of that will be trouble. But then one end of it is connected with piston, so that end moves to and fro in sliding, pure sliding. The other end, this one, is connected to the crank and excludes pure rotation. So we reduce the connecting rod dynamically to a simpler inertial distribution which can be analyzed well. So this connecting rod will simplify the energy by reducing the connecting rod. So its inertia we try to represent by two muscles, M1 and M2 at the two ends. Okay. This end is called small end, this end is called big. Because of the obvious reasons that this is lighter and this is heavier. Typically, the center of mass of the connecting rod is more on the right side. So we try to reduce the inertial distribution, which is non-uniform, inertial distribution of the connecting rod by two muscles, M1 here at the end and M2 at the end. Now, what will be the equivalent M1 and M2? The equivalence is based on the understanding that under the same resultant force system, the reduced or equivalent connecting rod should execute the same motion. So that is a step for the equivalence. So for dynamic balance, it should be a dynamic equivalence. It should not be balance. Dynamic distortion. It should be dynamic equivalence. For dynamic equivalence, which means same motion under the same force system, whatever is the F resultant force at offset E from the center of mass. So under that force, the CV should have the same motion, AG, F by M, and FE is the moment about G. So FE by J, moment of inertia, that should be there. So with F at an offset E, whatever is the actual acceleration and angular acceleration of the connecting rod, the equivalent also should have. For that, what should be M1, M2, A1, A2? So they should satisfy these relationships. Total mass should be same. The resulting CG should be at the same point, and the total moment of inertia should be same. So these three are the conditions. Now, if all the four things M1, M2, A1, A2 were in our hand, then we could happily satisfy these three requirements because four parameters can satisfy three requirements very easily with one of the parameters to pair which we could choose that way. But here A1, A2 are actually not in our hand because G is at some point wherever it is, we can change it, that is the connecting rod. And A1 is basically the distance of G from this end, and A2 is the distance of G from that end. So that A1 and A2 are already settled, we can't choose them. That is, we cannot adjust them in order to satisfy. Now, three requirements are here, out of which which have to be satisfied with four parameters, A1 and A2, two of them are already sort of given. So we can play with only A1 and A2. So playing with only two parameters, we can never really satisfy three requirements completely. So we make a compromise. We say first two we will satisfy, and the third one we will see what can be done. So for approximate representation, we say these two we satisfy. And when we try to solve these two for M1 and M2, we get very simple expression. I mean, this is just you can without any difference. So, for example, from here you get M1 by A2 equal to M2 by A1 equal to Poisson constant, and then insert that here, and from that you get It's very easy. Or you can filter that this is true. You add the two things, you get MC. And you multiply A1 with this and A2 with this and you filter. So these two are very simple. So you get this. Now we know that if we insert M1 and M2 here, these two expressions, then this doesn't have to be satisfied. So whatever is the error there, for handling that, we can later apply a correction. So now this mass M1 at the small n is then included along with the total mass of the piston assembly, piston, buoyant ring, or whatever it is with the piston, which moves with the piston like this. Okay, and take all those masses, including this M1 with them, and call it the reciprocal. On the other hand, the big end mass M2 you include with the crank, and the crank is actually manufactured with a certain shape with a counterweight on the rear side, so that the total weight of this crank thing, including the big end mass of the connecting rod here, the whole thing is so organized that its CG falls at the fixed point. This is the complete balancing of the crank. The crank is completely balanced. Its CG falls at O, which is the fixed point, which doesn't move, doesn't have any acceleration. So the force and linear acceleration of the crank CG, that equation is sort of made. So it won't be. So the crank will be analyzed only for rotation and rotational dynamics. Thus, a troublesome connecting rod is rendered massless digitally because one part of its mass is taken with the piston assembly, the other part of the mass is taken with the crank. Now, the connecting rod itself is a massless rigid plate. For the analysis purposes, it will be okay, except for the approximation, in which this condition was not satisfied. For more accurate analysis, in later correction terms, we will add up at the appropriate expression. Even if we do not add that, the inaccuracy will not be too much. Okay. Now, finally, we start considering the forces and moments. And only on the piston and the crank, because connecting rod is a massless rigid. So, in that, there is not much to analyze. Now, take the forces on the piston clusters because the small end mass of the connecting rod has got added to it. So you see, the piston moves like this in a cylinder. So this is the side from which the gas pressure is operating. So that's why I am showing like this. And the positive direction is this. So when you write x double dot, its positive sense is in this way, in this direction. So the inertia force will be minus m vec, m reciprocating x double dot, that will be this way, and that is with the A, you put that. So this whole thing is one side, and this Q, which is the force from the connecting rod on the piston. So equate the two, and you get this expression of Q. And this normal reaction, you don't have to bother about, because this normal reaction will be just the sign component of, okay, this minus sign should be this way, and this way. So this minus sign. So it is just the value of the normal reaction. The vertical component will help. The horizontal component gives you the force in the connecting. Now this massless connecting rod acted upon by just two forces, one from the piston and the other from the crank. and since there is no mass, so inertial force will be zero. So under the two forces, it has to be balanced, and therefore this force Q from this end will get transmitted all the way up to the fan. And now we have already discussed that by a special construction with the counter, the entire mass of the fan, including the big end of the connecting rod, is balanced. So as we have it see here, that we have already discussed. So when you now consider the fan, if CG is here, and if you take the free body like this, then the joint reaction at this point will be exactly equal to Q and opposite. So together they will have a turning. This is what we want, because this is what will give us the output torque, which will turn the wheel against the opposition. So that will be this Q times sine of this angle. And this angle is phi plus theta. That is the angle. And the exterior angle is equal to the sum of the two interior. Otherwise, you will say that this angle on this side is 180 degree minus this. So whatever way you do, you get. And then take that earlier Q expression from here to here, from this thing into this R divided by, okay, so this upper thing divided by cos phi was the expression for Q multiplied with R sine theta plus phi. For a vertical engine, in which the piston is up at the top, okay, along with this, there will be a rudder. Otherwise, everything is the same. And accordingly, yeah. Now, so you get the expression for the turn on the wheel. There is a crank. The crankshaft is the shaft which gives the power to the utility when you are utilizing the power. Now, we may like to apply a correction term on M based on that third equation which there was the. So, what is the error in, in the moment of inertia that we were tolerating till now? So, actual J minus effective J. Effective J means the moment of inertia of the two mass addition and so the true moment of inertia is mass of the connecting rod into K square. So K is its radius of gyration. Minus effective moment of inertia is M1 A1 square plus M2 A2 square. M1 at distance A1 and M2 at distance A2. Now, when we put that M1 and M2, which we determine, which we have been using here, and simplify, we will get this as simply MC A1 A2. Because if you take MC A1 A2 common, from here you get A1, from here you get A2, A1 plus A2, that cancels the denominator. MC A1 A2. And this is MC K square. So this is delta J, the error in the moment of inertia. And moment. So error in the moment will be error in the moment of inertia into the angular acceleration, phi double. Because phi shows the angular position of the connecting rod, so phi double. So you know phi, sin phi we express in terms of sin theta. So that expression, if you differentiate twice, getting something for phi dot and something for phi double dot, and then use our earlier assumption of theta double dot equal to 0, and then the smaller part of the rest will be in terms of theta phi dot square and theta dot square. Phi dot typically will be less because this angle will not change too much because this is long and this is short. On the other hand, this angle theta will change much. So theta dot will be more prominent compared to phi. So phi dot square, if you neglect in relation to theta dot square, then finally you get this you should make. You differentiate religiously, then smaller terms you neglect, dominant terms you retain, and the most dominant terms you use, and you approximate. So this delta j into this phi will give you the correction in the moment. So whatever moment expression we found earlier, with that, if you add this correction, you get a better estimate of the turning moment that is developed at the junction. And this is what is of our use. With this, we will proceed further. And as in this act of proceeding, what will be important to know is that this Q, the force through the connecting rod, and this moment M are functions of theta. Hence, with a constant W, within a cycle, it will undergo a cyclic variation with theta. Now, this cycle is not necessarily by a 2 pi rotation of the time, that is diagonal theta. Time turning will be 2 pi. Yes. But then the cycle of the engine is the entire turning by which one thermodynamic cycle goes through. So that may be 4 pi or maybe 2 pi. 4 pi if it's a four-stroke engine, 2 pi if it is a two-stroke. You know that there is one round of power production from the burning of the gas or whatever is using the power in 4 strokes, that is 2 crank cycles in 4-stroke engines, and in 2 strokes, there is 1 crank cycle in 2-stroke engines. So accordingly, this cycle variation of theta takes place over cycles of 4 pi or 2 pi of crank cycle. So this cycle variation of turning moment and the associated other issues and requirements we will study in the next.